Right. Let's begin here. I want to welcome everyone to this webinar and thank you for joining. Today's webinar topic is laser vibrometer for vibration measurement and modal analysis. My name is George Farah. I'm a business development engineer here at ATA Engineering. I'm based out of our Denver office, and I'm very happy to be joined by our very own Gabe Cruz for this topic. Gabe is a very experienced Testlab user and Siemens certified expert. Before we dive into the actual content, here's some housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, please type them into the chat and we'll have the presenter answer them at the end of the presentation. This webinar will be recorded and available on our website and our YouTube channel. Before I hand this to Gabe, I want to go over a quick overview of ATA Engineering, who we are, and how we might be able to support your team. So ATA is a high-value engineering services company helping our customers tackle the toughest problems. Engineering services make up about 70% of our business, with most of that work focused on the aerospace and defense sector. As you can see here, we have our hand in many different industries, including themed entertainment. So who are we? Well, we're a highly skilled employee-owned company with a full-time staff of around 220 people. Most of them having an advanced engineering degree, as you can see here on the right. We have 9 national offices across the United States. As I've mentioned before, we have years of experience focusing on design, analysis, and test, providing high-value engineering services and great quality. This includes everything from structural analysis, design, dynamics, thermal, vibroacoustics, and fluid dynamics, and much more. Test-wise, we are the leading independent modal test group in the United States. We have a lot of experience flying our team to the test article location and to conduct ground vibration testing, and using that information to help drive model design. We talked about the engineering services side of the business, and now that leads us into our software side. We are a Siemens value-added reseller, also known as the Siemens VAR, who not only sell the product, but we also provide software support and training to our customers. We really focus on products and solutions that we use in-house, primarily on the design, analysis, and test side of things. For example, NX we use for design, FEMAP, SimCenter 3D, and Star CCM for simulation. And for test, we are the first and now one of the only Siemens partners in the United States that can provide SimCenter testing in hardware and software. One thing that sets ATA apart is that we sell what we use, and because of that, we've seen past customers truly appreciate our expertise with these tools. This has been proven over and over again through our hotline support, where you're actually speaking with a well-versed and experienced ATA engineer. In addition, we teach a variety of classes primarily dealing with simulation, and we actually generate all the Siemens training materials for Nastran as well. I want to encourage everyone to visit our ATA website. You can find all kinds of good information on here, including our technical support hotline for customers who have purchased software from us, as well as free resources, including past webinars, FEMAP APIs, white papers, and much more, all of which are available for download. And that leads us to our speaker, Gabe Cruz. Gabe received his Bachelor of Aerospace Engineering from San Diego State University and his Master of Mobility Systems in Engineering degree from Kettering University. Throughout his graduate schooling, he worked on projects sponsored by the National Science Foundation, Cummins Meritor, and McLaren Golf, focusing on modal analysis and finite element modeling. As part of ATA's value-added reseller business team, Gabe works with customers and prospects to define technical testing-led solutions based on their engineering goals and needs. He also assists with customer supporting issues on ATA's technical support hotline and supports general testing efforts for ATA and our customers. That being said, Gabe, take it away.
Awesome. Thank you, George. I appreciate the intro. Let's replace the share. Alrighty, so let's get into the technical content of today's presentation. So we're going to again be looking at laser vibrometer measurements for vibrational measurement and modal analysis. So we're going to go over what is an LDV system, kind of how they work, their principles of operation, all you need to know just to get up and running with the laser vibrometer. And then we're going to look at it through the lens of an environmental control case study. So we're going to look at some vibration control test data, and we're going to do a little bit of analysis of that data inside of Testlab and Testlab Neo today. And then I'll give you guys a brief conclusion and give you guys back the rest of your day. So what is a laser vibrometer? So, an LDV system, or a laser Doppler vibrometer, is a non-contact measurement device that can measure the vibration of a surface of a structure utilizing laser technology. So it utilizes the Doppler effect and principles of interferometry to measure the surface vibrations, the velocity that is being created on a surface at individual scanning points. And we're going to go in depth into the Doppler effect and interferometry later into this presentation, not so deep into all of the mathematics and theory of it, but just enough so that you can understand how this will affect your measurements and how you can utilize these tools in the future. So we were talking about laser vibrometer systems, but there's also a scanning laser Doppler vibrometer system, or an SLDV system. And this system's a little bit different in that it can measure various different points on the surface anywhere where the scanning heads can see. And so all you need to do is define the geometry of your structure, and then you can define a measurement grid, maybe outlining the perimeter and define how many points you want to measure on that structure. So, what is the laser vibrometer used for? So, it could be used across a wide range of industries: the automotive industry, aerospace, naval and marine, and even more, such as electronics and going into even ultrasonics. So, it's serviced by a lot of industries, but there's a lot of different applications once we get into them, such as in the automotive industry, you can do your drivetrain vibrational analysis. So looking at the operational shapes of your drivetrain in motion, that's kind of what um, this image here in the top left is showing. It's also very powerful tool for end of line testing. If you know exactly where your structure is going to be, you don't need to use a scanning laser system. You can use a single point system and measure the tolerances or how it's vibrating due to a certain condition. It can also be used for brake acoustics as well. In the aerospace industry, these applications aren't quite specific to aerospace. Some of these are done in automotive as well, such as modal analysis or monitoring vibration control testing. One that is a little bit more exclusive to aerospace, though, is looking at turbine blade stress and strain analysis. So, being able to look at what is the in plane shear experienced on one of these blades in operation. For the naval and marine industries, we can see this as a powerful tool for measuring non-destructive testing of composite materials. So if you can excite that composite material with an ultrasonic wave, the scanning laser system can determine if you are experiencing any internal defects that are very difficult to determine. And even more with electronics, MEMS devices, microscopic measurements, a whole wide range of uses for laser vibrometers. But why would you actually want to use a laser vibrometer? So there's a lot of different advantages to other measurement devices when you use a laser vibrometer. Probably one of the biggest ones is going to be that it is a non-contact measurement device. So if you're measuring on lightweight components, if you're familiar with your modal testing, if you add an accelerometer onto your structure, that's going to add some mass onto it. And we know that the natural frequency is equal to the square root of k over m generally. So that is going to change the dynamic response of your structure. So we can negate that by, well, a laser doesn't weigh anything. And if we're able to determine the vibrations at that same exact point, that is an advantage over, let's say, the traditional accelerometer. The other pro of using a laser vibrometer system is that it has a higher density of measurement points. It can virtually have an infinite number of measurement points. It kind of depends on how long you want your test to take. Because if we think of this, let's look at this turbine blade right here. So each of the points where those lines are intersecting is a scan point. And if we wanted to characterize all of those different points utilizing a standard method, well, we would need, let's say that's 100 points, we would need 100 accelerometers. So with that, we're able to have better spatial resolution on what kind of stress and strain concentrations we are seeing in this turbine blade. And we can also, with the laser vibrometer, measure up to extremely high frequencies. I'm talking about the megahertz of frequencies. For maybe a little bit more specialized applications, maybe for noise, vibration, and harshness, we're really only carrying up until about 21, 22 kilohertz. So there's a lot of different types of laser vibrometers. So as I was mentioning before, if you're more concerned with single point testing, you might want to use just one of these single point accelerometers in end of line testing, or you can create an array of all of these laser vibrometers if you run a very similar test every single time. But then we also have our single scanning heads. So these are very useful when you need to measure your out of plane responses. So displacements, velocities, or accelerations on your structure. This could also be used for non-destructive testing we're talking about. But this system right here is also equipped with a range extender. So if you need to be scanning on a very large surface area or a structure that is very far away from you, particularly useful in the naval and structural slash building applications. I think you can kind of see, I think there's like a cell tower here shown on this computer screen. If you're doing operational modal analysis on very large structures, maybe a range system would fit your need a little bit better. And then we've got the classic 3D vector vibration scanning system, or this 3D SLDV system for when you need to capture your out of plane and in plane responses. So if you're looking at describing your shear concentrations in those turbine blades, for an example, you're going to need that 3D system to have not just your out of plane, but your X and Y in plane. And then there's also these kind of base station vibrometer systems, which are for more specific applications outside of noise and vibration, such as characterizing MEMS devices with microscopic measurements, or for surface metrology, characterizing the finish of a structure. And there's also a lot of different laser vibrometer competition out there. There's right here, I'm showing mainly from Polytech, but there's also vibrometers made by other companies such as Optimet. So let's get into kind of how does a laser vibrometer work? What goes into it? What are the principles of operation? So how does it work? So going back to that first slide, I said we're leveraging the principles of the Doppler effect and interferometry. So what is the Doppler effect? The Doppler effect is the change in frequency of a wave that is the result of a relative change in motion, or we'll just say in this instance, the speed of the source and the receiver. And I'm going to play a video right here that's going to illustrate the Doppler effect. It's going to have a fire truck driving towards us and then away from the cameraman. So as the fire truck is coming towards us, we can hear that it has some frequency. And as it's going to go right past us and shoot on by, we're going to see that frequency decrease. So why is that? So the sound wave has some inherent frequency, but when the truck is driving towards you, the waves are coming faster, so it appears to be higher in frequency. Whereas when the truck is driving away, that wave is taking longer to reach you. So it sounds like that wave is lower in frequency. So when we're kind of looking at the Doppler shift effect, we're really concerned about that, how that velocity is affecting that frequency. And so the laser vibrometer uses a high frequency laser to measure the change in frequency of a backscattered light wave based on the velocity of the structure. So this is kind of what is going on internally to the laser vibrometer. We don't really need to discuss all of the components in here, but what we really need to care about is that our laser is being generated in here, and then it's getting split down two paths. So we have this reference path here on the, we'll call this the left, and then the beam that is getting measured here shooting onto our structure through the lens. And so when the measurement beam, this is it being transmitted from our vibrometer, is reflected back upon hitting the structure, the light wave is going to have a frequency shift due to the change in velocity of the structure due to some excitation that we're providing in. And so that is that Doppler shift effect. And so now it's getting reflected. The light is being picked up back by the laser vibrometer, and it's being added together from our reference beam. And so this is going to create some modulation in our signal that is then going to be picked up. And then that resulting modulation is going to be deconstructed by the software. And so we're able to pull out that new signal based on the principles of interferometry, which we really don't need to get into today. So again, some of the more important factors you need to keep in mind with the laser vibrometer is your 1D versus your 3D measurements. So if you want 1D measurements, that out of plane response, or we'll just say Z, for example, you can just need one scanning head. But if you need your in plane, you're going to need three heads for triaxial vibration data. And another interesting factor with these laser vibrometers is you can actually stitch together multiple measurements for the same structure. It takes a little bit more work, But what you can do is if I want to have, let's say, a little bit more resolution here on the tail, maybe I'm concerned about the control surfaces on my wing, I would put my laser vibrometers in a way so that I can have a more defined point resolution. So I could say I design a perimeter around my control surfaces and then I can increase the point density that's in there. And maybe I want to do some designated measurement points on the structure. And then I could stitch together all of these measurements to have one really well defined model across this whole glider, for example. And so with that, we can have pretty much as much scanning points as we want across this measurement for one structure. But what you need to keep in mind as well, how much time is that going to take you? Because if we think about our assumptions during our structural dynamics testing, we're assuming that our structure is linear time invariant. We won't go over linearities, but what we need to keep in mind is time invariance when utilizing a laser vibrometer because scans can take minutes or even days depending on the application. What are your scanning settings? So what you need to keep in mind is what kind of frequency resolution are you looking for? How many points are you taking per averaging? And then the number of scan points. So we have like a general equation that we can say here is that the length of test is equal to the time it takes to obtain one measurement. So if we say we want zero point 0.1 hertz of frequency resolution, we're going to need to measure 10 seconds. That's from Rayleigh's criteria. And we'll say we'll measure 10 times for 1 point to get 10 averages. Okay. So we already have 10 seconds. We're going to measure 10 times per point. And then let's say on this beam, we're measuring 100 different scan points to have this nice resolution here. Well, that 100 seconds per point times 100 points is 10,000 seconds, or it's almost about 3 hours for just a simple beam structure right here, if you want that frequency resolution. So adjusting these parameters based upon your testing needs, how the duration of your test, how long you have with the test article is going to be extremely important. And so here's a little bit of information about the laser vibrometer that might be useful to some. The Polytech laser vibrometer uses an infrared sensor, so it has a wavelength of 1550 nanometers, a frequency of about 193.4 terahertz, but the maximum measurement frequency we're looking at is 32 megahertz. Depending on your application, you might not need to go that high in frequency. I think for most noise and vibration issues, we're looking at generally sub, again, 22 kilohertz, definitely less than sub 30 kilohertz. And maybe one of the most important factors, the laser screen. I jest, but one thing you need to keep in mind when doing a laser vibrometer measurement as well is how well is your laser vibrometer picking up that backscattered light wave? We saw that there was that photo detector inside, but how can we actually ensure that we're having good signal quality with the laser vibrometer? Excuse me. But what we can see here on the back of the laser vibrometer, there's this signal bar, the signal gauge, and what it kind of tells you is how well is the light reflecting, how well is it getting picked back up by the vibrometer. And so one of the key factors to keep in mind is does your structure have specular or diffuse reflections? And this is going to determine how the light is reflected off. So specular reflections can typically result in low signal levels unless you have the laser vibrometer perfectly aligned. So this specular reflection occurs when the light bounces directly off the structure. You can think of this as when your structure has a very shiny metallic finish or a mirror-like surface. If you've ever been sitting and someone's on their phone in the car and then the light is just so happens to be at the perfect angle where the sunlight is reflecting right off the phone into your eyes while you're driving, that would be an example of like a specular reflection. A diffuse reflection would be when the light hits the structure and it spreads out. So if you're kind of, I guess, if you're in an office building, typically the walls you're going to see around you are going to be diffuse reflections, unless you live in one of those carnival mirror mazes. Uh, so you want to make sure that your signal has a very good, uh, you're getting very good signal levels. So you can either put tape onto your structure if you're experiencing specular reflections, if you know exactly where your scan points are going to be. But if you don't have designated scan points and just want to define a component area, then maybe some spray paint would be a good idea as well. So now we'll look at the environmental control case study. So right here, we've got this PCB circuit board. This is coming to us from a paper from some of my colleagues, Caleb Heitkamp and Ben Martins, from their paper Monitoring the Response of Electrical Components During Environmental Vibration Tests, utilizing a scanning laser Doppler vibrometer. And so the objective of this paper was to measure the difference when measuring utilizing a laser vibrometer system and an accelerometer to collect the vibration data on these small components on this PCB during a random control test. And you can see here on this image, for example, we had predefined scan points. So we're able to put down tape exactly where we're going to measure on the structure to make sure that we have diffuse reflections, that we have a good signal quality for our vibrometer. And so this is kind of what the setup looks like right here. We've got the PCB mounted onto our V830 shaker. We have our control accelerometer mounted very closely onto the shaker, but near the corner of the board. And then we have had our laser vibrometer mounted directly overhead to capture that out of plane response on the PCB. So a little bit of information about our laser vibrometer here at ATA. We have the Polytech PSV 400 system. It has a helium neon laser with a wavelength of 633 nanometers. Our vibrometer can measure up to 10 meters per second of velocity, and then our maximum frequency is 25 kilohertz for most noise and vibration applications. And then the second most important quantity, the laser's red. But we were testing it with this random vibration profile right here. This PSD is increasing till about 80 hertz, has a constant level till about 250 hertz, and then is decreasing logarithmically till about 2000 hertz. And so what I wanted to do is take the data off that vibrometer and show you how we can do some operational modal analysis from that SLDV data. So I'm going to stop sharing that. And what we can do is right here, I just exported the data from the laser vibrometer, and this is what we have. So we have all of our scanning points shown right here. So we have all of the different components on the PCB. So this right here on the right-hand side is component number one. Directly to the left of that is component number two. In the middle right here, more towards the left-hand side is component number three, four right above that, and then five right above that. So this is the geometry we were able to pull off. And right here in my run one, this is all of the data I was able to get from it. So we have our auto powers, our spectrums for our measurement points, our coherence functions, and our cross powers. We also have some PSDs, ESDs, and some frequency response functions. So for these cross powers and these frequency response functions, we're taking the data as referenced to our control accelerometer. So we had our control accelerometer plugged directly into the SLDV system as well. So what we can do is take a look at these cross powers. If I want to look at a few of them at a time, I can select 3 cross powers, and then I can just kind of scroll through and see what is going on throughout our 2000 hertz frequency range. So we could look at it in amplitude. Maybe we want to look at it logarithmically. And then we can just click through and see what kind of responses we were looking at. But I want to take a look at our operational deflection shapes here. So what I want to do is I'm going to add these cross powers into my input basket, and I'm going to go down to this animation pane. So on this animation pane, there is kind of a lot here. So we've got our geometry here shown at the bottom. We have our processing here on the right, depending on which measurements we want to do. If we want to have a single or double cursor once we have our data, our band processing. If we have a roving excitation, we could switch our measurement columns here. And then we've got these operating points, which we'll take a look at here in a little bit. And so I need to select what kind of functions I want to use for our operational deflection shape viewer. So we have a whole wide range of different accepted function types. We can use a waterfall, which is particularly powerful, especially if you're measuring RPM, because then now you can pick exactly where on the color map you want to be measuring based on frequency and RPM. But today we're going to use cross powers. So right now it's currently selected on my project, but let's select it on my input basket. So I have 40 different points right here. And what we can do, let me expand out this graph. So this is the envelope of all of our cross powers added together. So we're taking the maximum out of all of them. And this is my slider, which is going to affect the viewer down here. We won't quite start the viewing just yet. We'll just look at some frequency range. So from 36 hertz to 623 hertz. And I can have a preview of my function. I can have the summation of all of them. But let's take a look at some of these peaks. So if I see this peak right here, this is the envelope at 142 hertz. I can see that, yeah, that looks could be a kind of bending mode here, but let's see a little bit before. Okay, yeah, that seems to be pretty rigid, going up in frequency. Yeah. So maybe I want to take a closer look at this 141 hertz. I also have these arrows down here, which will move the frequency just a little bit. So I can kind of put it right here, a little bit closer onto that peak. So I go back to my operating points right here, and I can add in this operating point. And maybe uh, I can add a little description right here. I'll call this first mode. And then we'll go up in frequency to this next peak right here. Is at 214 hertz. And we can look at the shape here. There seems to be some pretty high excitation on component number two, and maybe there might be some breathing effects here. Let's just add an operating point. Maybe I want to take a look at it a little bit later. We can call this maybe second mode. And then right here, I've got another really big peak. Let's see what's happening here. Well, we can see that this particular point is dominated by the response of this 13th point. Well, maybe I want to see what effect point number 13 is having on my measurement. So I'll go back to my data selection window. I can look at specifically point number 13. Let's just do a little bit of a zoom in right here. And we can see that 13 is what's causing this whole part to envelope. And we can see that our summation of all of our signals, this green line down here, we're not really seeing that much excitation at this frequency. So what happens? We can just see what happens when I turn off point number 13. Yeah, that completely reduced the peak right there. We have very low excitation frequency, or very low excitation due to this frequency. So, okay, maybe I want to leave point 13 off for right now. And then we'll go on to this next peak at 245. Okay, yeah, there definitely seems to be some breathing effect here. So we'll add in one other operating point. And once I've got a few operating points, I can use these fast forward and kind of rewind arrows to kind of cycle between each. So I'm at that 141, I'm at this 214, and then I'm at this 245. And so I can save this as a processing set, or I can just delete them all, which I'm going to do for right now. So I'm actually going to close out of this because I'm going to open up the same data set inside of Testlab Classic. And what we're going to do here is do some operational modal analysis. So I've got the same process, the same file opened here in Classic, and I'm going to add those same cross powers in my input basket for our operational modal. If we had time data measurements, we can actually separate out what lengths of time we want to be looking at in this operational data collection. But since I already have my cross powers because I got them from my SLDV, I just can go straight on ahead to my operational data selection. And so I can see here the summation of all of the cross powers, and I can scroll through and see what each one looks like compared to the sum total. And I could pick from my active section that there's a lot of data here. So since I'm adding them from my input basket, and I'm only caring about that out of plane direction because we're only utilizing that one singular scanning head. And so I could save this cross power set. I can even enable the geometry when I'm scrolling through to see which point is affected by what. I mean, we can go back to that point number 13 here. We can see it on this geometry display at the bottom. But okay, so I've got all my points set up. No need to make a cross power set quite right now. And then I'll go straight to my Polymax window. And so from here, if you're familiar with traditional modal analysis inside of Testlab Classic or Testlab Neo, you're going to select your frequency band that you want to take a look at. So we'll just go from 55 to about 800 hertz. We have our summation. We've got our selected function if we want to take a look at some of these other ones. We can even look at multiple on the same graph. But now I've got that my range that I want to take a look at, we can go straight to our stabilization. So I bumped this up to our 80th model order. And so all of these S and Vs, um, pretty much what we need to keep in mind is we want to select our stable modal vectors. So if it's an S, that means it's a stable pole. A V is an unstable pole. We don't want to be selecting this. So we can go and just kind of peek pick, make sure we're clicking on our stable modal vectors. Okay. And we can take a look at what these are going to look like. We could pick this one, but we'll just go straight ahead and pick these 11 modes for right now so we can analyze. So then we'll go into our mode shapes and we'll call this a new processing name. So we want to call this, we'll just call this live demo. And so I want to calculate with these new modes, and now we can display them here on this display at the bottom. And so it was able to pick up these kind of same modes that we were seeing when we were kind of just scrolling through our operational deflection shapes. So that 141, that 217, that 245. And so we can go back to our navigator. Wow, there seems to be a lot of excitation here on component number 2. And then we can see that our live demo operational mode set has been added here. And so what I want to do is just quickly save right now. And then we can exit out of this and we'll go back into Neo. So this is just showing that we have parity between Classic and Neo. If you want to switch back and forth, you could, or you don't have to. I could have done the modal analysis inside of Testlab Neo by utilizing the frequency response functions referenced to that control accelerometer. But I just wanted to show you now that we have that live demo mode set here. So we could take a look at it inside of Neo as well. So what I want to go back to, let's re-add those cross powers back to my input basket. I want to go back to that operational deflection shape viewer. So we've got here our data selection. We'll go back to our input basket, make sure we're on cross power. And one of the features that I want to show is we can automatically select peaks. So let's say I want to take 5 peaks from this graph. I want to look over just, let's say, the 350 to 800 hertz, for example. And then I can select my amplitude threshold that it has to pass for it to select, and then this kind of percentage gate value. So I can bump this up. We can go, let's say, 30. And so it's going to pick some peaks right here, just only where we have peaks in the graph. And so I see I wanted only 5 peaks. I've got 5 peaks right here. We can save these operating points. So if we go back to desktop, we have this ODS processing now. So these are the shapes that I was getting from that deflection shape viewer. These are the saved ones here. And so what happens if I want to do a little bit of comparison between the data that we just obtained from Polymax and this set that we obtained just now from this viewer? So we can go to this modal tab and we can do this modal correlation with our deflection shapes and the operational modal. So we'll add the live demo here. We'll do this operational mode set. We'll set this as our reference geometry or a reference set. So we have the 5 sets, the 5 right here from our working set, which is coming from this ODS processing. And we can kind of see how well do these results correlate to one another. Maybe you don't want to correlate your deflection shapes to what you were pulling out from your modal analysis. But if I wanted to compare how similar are the shapes that I obtained from my deflection shapes, I can do this working automac. And so it has pretty good uh, cross values, off diagonal values here. Only 14 here, 14% for our correlation. We can look at the reference set automac as well. And we can see that this mode 2 and this mode 3 are pretty similar to one another. They have about 80%. And then up here, our other off-diagonal terms seem to be pretty good when dealing, especially with operational data. We're only utilizing the cross powers. We do have some significant similarities here between modes 4 and mode 5 at 45%. So if I wanted to kind of examine the two mode shapes identical, animated next to one another, I would just need to add both the reference set and the working set to be the same mode set. And then go back to this Mac tab. Perfect. My mouse scroll wheel is not quite agreeing with me, but that's all good because we can get right back to the presentation. So again, this paper was about what is the difference between measuring with an SLDV versus an accelerometer. So here, right here is the graph that shows the FRF peak frequencies and magnitudes for each fundamental component mode. So those 1, 2, 3, 4, 5 components right here. So 1, 2, 3, 4, and 5. And so I put too many animations. For components 2, 3, and 4, we did see some changes. So for components 2 and 4, we saw an increase in the amplitude of their response. Component number 2 had about a 1/3 increase in its response, whereas component number 4 saw a drastic increase in the level of response. I don't have my laser pointer on. Whereas component number 3 actually had a reduction in the amplitude here. And we saw that there was a increase in the natural frequency when measured with the SLDV. So these ones are the SLDV, these are with the accelerometer. And component 4 was pretty similar one to the next in terms of the component mode when looking at the frequency content. Component 4 was a very small component, so that's why we saw a huge increase in the level of excitation here on that component. Uh, yeah. So then we can actually take a look at component number 2. And we can actually take a look at that frequency response function and kind of see how we can determine that from the data. So these are, when we're comparing the two, we're going to look at the yellow and the purple lines. Or not yellow, orange. The orange line is with an accelerometer. The purple line is without the accelerometer. And then the green line is the accelerometer, but in a different scale factor. So not quite comparable to what we're looking at. So looking at the orange and the purple, once we're getting past this 1000 hertz, we see that there is kind of a lot of noise in the data. That's because our PSD was decreasing until about 2000 hertz. We're just not getting as much resolution in our data. We're not exciting it as hard as we are in these regions to see good coherence values. But what we can see right here at around this 500 hertz range is that uh, there is a difference in this mode right here. We do see a reduction with the accelerometer. That peak is also seems to be a little bit more spread out, whereas with the laser vibrometer, it seems to be a little bit sharper, also increased in frequency and a higher amplitude. So to conclude the webinar today, the scanning laser Doppler vibrometer leverages a high frequency laser and the Doppler effect to measure vibration all across the structure. Scanning points add time to your measurement, but allow for a lot better spatial resolution. Some of the advantages that we saw with the laser vibrometer is that in non-contact measurements, it negates the effect of mass loading, getting you to a more accurate value of what kind of responses you're seeing when especially dealing with those real lightweight components. And then we saw that the data obtained from a scanning laser vibrometer can be exported for use in a wide ranges of softwares, but including but not limited to Testlab for operational modal analysis, just plain old modal analysis, vibration control monitoring, and so much more. And I want to thank you all for attending today's webinar. If you have any questions, please do reach out to me. My email is right here in the bottom right-hand corner. I urge you to check out the website. George had some really great links to share before. And thank you, everyone. And I don't think we had any questions in the chat. We'll give it another 30 more seconds if anyone has any questions before we conclude today's webinar.
Okay, looks like we got something from Colin. Colin, if you want to type it in, I can read it out loud and we can ask Gabe. All right, Gabe, I don't know if you can answer this, but how much does a system like the one you demonstrated cost?
It depends. Depends on what your needs are. I would say if you need a 3D scanning system, you're kind of looking in, I can't say like a generalized number because if you're looking at the encoder in the system as well is going to determine your maximum frequency content, the maximum uh, velocity that you can measure. But I will say around the 500,000 to at least a million if you want a 3D system. I'm not so familiar with the cost of a 1D system, but that's kind of the ranges that you're looking at least for the 3D.
All right, additional question from Colin.
Yeah.
Did the
Did
one
the one
vibrometer
vibrometer?
system
eh,
measure all the points on the PCB?
So on this test, they measured only the points where you see in white, which is the ones that I was showing in Testlab. So all of the points that we were analyzing inside of Testlab all came from the laser vibrometer. But if we wanted to, we could define if we just it wouldn't be as ideal for a structure like this because we can't spray painting it would ruin it. But if we wanted to, we could spray paint this component number two, define the perimeter of it, and then include maybe like 100 scan points on here to have better spatial resolution of this component. Perfect. I don't think we have any more questions, George. I think we're ready to close out the webinar.
Yeah, I would agree.
Awesome.
Thank you all for joining. Gabe, great work, and be sure to catch us on YouTube later. Thank you guys.
Awesome. Thank you, everyone.